Hello again. Today's topic is going to build on the exponential function topic that you saw recently, hopefully yesterday. And today, when you're watching this, should be Thursday. It's a full period. We're going to talk about a branch of this exponential function business. Friday is, if I remember right, is a half day for you guys. So there it'll be just a chance for a little bit of review and not a brand new topic. For this topic today, I'm going to be juggling between 3 different screens. So be prepared for some chaos here as I try to manage my clicks. I have up the slides from the earlier topic from yesterday or the day before, whenever the heck that was. The day I recorded it is not the day you watched it, so I'm totally confused at this point. But you learned about exponential functions, things like this, right? A base, some fixed number raised to a power where the variable x is actually in the exponent, right? So not x squared, but something like 2 to the x. Okay, so you've seen these now, these exponential functions, and what you saw was that sometimes, like in the case for 2x, the value of the function goes up and up and up as x gets bigger and bigger, right? 2 to the first is 2, 2 squared is 4, 2 cubed is 8, they're getting larger. That is exponential growth, as opposed to this 1/2 raised to the x formula. As x gets bigger and bigger, the numbers coming back from this are going to get smaller and smaller, because 1/2 squared is 1/4. 1/2 cubed is 1/8, right? So the bigger x gets, the smaller the function values get. That is exponential decay. So basically that rule is if your base is bigger than 1, then your function's going to get larger and larger and larger, and that is exponential growth. If the base is less than 1, now we don't want negative numbers, so that's why the wording on the slide says that b needs to be 0 and 1. We don't want to worry about negative numbers, but for base values that are less than 1, when you start raising those to higher and higher powers, the value of the function is going to get smaller and smaller. Okay, that is exponential decay. I will leave it to you to decide why we don't want the base to be 0 itself. The answer is because that would be a boring function. And also why we don't want to worry about the base being 1. Because 1 to the x is also a boring function, but you can think about why. So here are just some random grabs of exponential functions, and our job is to just kind of scan them and decide which one's growth and which one's decay. And remember, it's whether the base is bigger than 1 or less than 1. So this upper left version, 3.1 to the x, well, the base is 3.1, that's bigger than 1, which means that as x gets bigger and bigger, like 3.1 squared, 3.1 cubed, the value overall is getting larger and larger. And remember, I'm using, x values like 1, 2, and 3 as samples, but that exponent could be anything. We could take the number 3.1 and raise it to the power 2.42798, right? That would give a numerical result. You would need a calculator to say what that is, but it's possible. 4/3 to the x. Okay, well, 4/3 is bigger than 1 last time I checked, so that's still going to be exponential growth. Here on the tail end on the right top row, 0.15 to the x. Now that's going to be exponential decay because 0.15 is less than 1. 2.9 to the x, growth. 3/7 to the x, decay. And finally 1.25 to the x, growth. Okay, now these are very generic representatives. What we're going to do, and you've seen graphs of things that look like this now. Remember, those are the swoops that either swoop upwards for exponential growth or that swoop downwards like a ski slope for exponential decay. Okay, we're not going to do that. Nope. I'm trying to scan through because yesterday we just did the functions themselves, and today we're going through to pick up all the lingo. So okay, never mind with these slides. I'm going to show you, is it this one? Okay, good. So in the folder for this topic in Google Classroom, there's going to be a little single page sheet for you that's going to collect a few varieties of exponential growth or exponential decay scenarios that we are going to use. The ones we just looked at on the PowerPoint slide, those are just very generic functions. They didn't have a purpose to them other than to be a function. A lot of times a problem has a story to tell, and so we are going to be able to generate exponential growth and decay equations based on what the story is telling, and then use that story to decide some new number down the line. So for this run through this, we're only going to look at the first two. This sort of generic exponential growth and generic exponential decay. I'll talk about the components of those in a minute, but on this handout there's going to be more stuff at the bottom: compound interest calculations, radioactive decay or half-life problems. Those are exponential growth and decay scenarios. We'll leave those for next week. Okay, and I believe Mr. Childress should be back next week, so we'll let him know exactly where we kind of drew the line in new content so he can pick up there. So what we're going to do is look at some exponential growth or decay scenarios, and we're going to decide which one of these two functions to use. Recognize that both of these functions end up giving us an exponential function, right? But one of the varieties will be the one that gets bigger and bigger. One will be one that gets smaller and smaller, and you can tell the difference because this top one takes this term 1 plus r and raises that to an exponent. So in this case, forget the a just for a second, I'm going to cover it there. That 1 plus r, say you have stuff like bacteria in a petri dish, and the population of that bacteria is increasing at 10% a day, right? This stuff, you're in a science fiction movie and this stuff is growing, right? We turn percentages into decimals. 10% is numerically 0.1. So whatever amount we start with, the next day or whatever time period you're looking at, if this is growing at 10% per day, then the next time we check in, the amount will be 1.1 times the amount that was there before. And then the next day, it'll be 1.1 times the second day's amount, and so on and so on. The population is going to get bigger and bigger. So if r is 10% or 0.1, this 1 plus r would be 1.1 raised to the variable t for time. That is exponential growth because the base is bigger than 1. If we have exponential decay, then like the amount of milk in my Frosted Flakes is decreasing at 25% a minute because I'm hungry. That means that we would do 1 minus 0.25 for 25%, so 0.75 raised to the t, and then that would show the amount of milk in my Frosted Flakes every time I check in, whatever time period that is. It's dropping by 25% each time. Okay, the a in front is just the starting amount. Right, so you take the starting amount and then you're either stacking up multiples of numbers bigger than 1, making that amount grow, or you're stacking up down here multiples of number less than 1, which is making that number shrink. Okay, so there's your exponential growth or exponential decay. So if it hasn't happened yet, hopefully if Mrs. Williams is still kind of helping you guys out, she can crank out some copies of this page to give you, or you can print your own somehow, or just take a picture of it, or whatever, screenshot something. But these are the two formulas we're going to use. And so what we're going to do is look at scenarios which, yes, word problems, that carry this information in it, and we're going to make calculations to answer a particular question. And this is always the never-ending conversation. Oh, when am I ever going to use this stuff in real life? And so somebody says, okay, you want to see? Well, here's a problem that gives you information and asks you to do something with it. And you say, oh, but I hate word problems, right? There is a fundamental conflict in the two objections that get raised a lot in math classes. But here we go. So let me find my other document. Okay, here we are. So scenario number 1. We have a painting. Its current value is $1,400, but that value is going to go up by 9% each year. That is exponential growth. we're going to write the function that builds this information in and use that function to find the value of the painting 25 years from now. Okay, so here we go. I have this ready. This is the generic exponential growth formula that was printed nicely on that summary sheet. A is the starting amount, R is the rate of growth, and T is the time gone by, and with those numbers in there we can crank out some final amount that we're after. So I'm going to flip to this next page and I'm going to jump back and forth a couple of times here. So the original value of our painting is $1,400. So, you know, in this formula down here that we're going to fill in, remember A is the starting amount, so in this problem, A is going to be $1,400. What else do we know? The value of our painting is increasing by 9% each year. Well, that's R, the rate of increase. Now, percentage-wise, we're told 9%, but we need the decimal version of that. And 9% in decimal, 9%, 9 per 100, right? Remember your Latin. Pretend you're a Roman, okay? Percent per 100, 9 per 100 is 0.09. And then we're asking, what is the value of this painting going to be after 25 years? So we want T to be 25. Okay, we load this information up, we run the calculation, and boom, out will come our answer. So we want A to be 1,400. We want R to be 0.09. Here's what I'm going to do here. If I drop that 0.09 into the R, this number on the inside of the parentheses is 1.09. 1 plus the rate of growth, and we want T to be 25. So our job is to get the value of this number. You're not going to do this in your head, right? This is a calculator job. I'm looking at my other screen. I should have had this ready to go. My recording bar is in the way. All right, now it's out of the way. Now I'm going here to a website that does calculations. You can, if you have a scientific calculator, go for it. So I'm typing in 14 times 1.09 raised to the 25th. And I'm not going to adjust my screen capture to see that, but I will tell you the result. It looks like the result is $12,072 and rounded 31 cents. So the 1,400 was in dollars and this is in dollars. So you push some buttons in a calculator on your phone. I think it's okay to have a device out for calculation purposes, or get a calculator, pray hard, whatever it is you have to do. Make sure that you can punch those numbers in and get this result back. Okay, after 25 years, this painting that was worth 1,400 is now worth 12,000, but 9% is a pretty good interest rate. Never pay that on a car or a house, but do try to get that on a bank account. Okay, let's do another one. Scenario number 2, the population of a town is decreasing at 1% per year. In 2020, there were 2,300 people. Write a function that describes this scenario and then find out the population in 2030. Okay, so in this case, I haven't prepared a screen yet because I want to do this basically from scratch. So this is exponential decay. So the way this goes, you can reference the help sheet. The original amount times, and then 1, which is if your growth is 0, you're just staying at 100% every time. So that would be a multiple of 1. For growth, we add the percent growth rate in its decimal form. For decay, we want to subtract that growth or that decay rate in its decimal representation, and then raise that to however much time has gone by. So in this scenario, let's see, the original population was 2,300. The interest rate, I'm writing this down, I'll show you in a second, is 1% per year. That is 0.01 in decimal form. And the T, we want to be a number that represents the year 2030. and that's as compared to 2020. Okay, so we are, oops, sorry, I'm not showing you the right screen, right? So the question says, what's the population going to be in 2030? But that's 2030 as compared to the starting location or the starting time of 2020. So load this up. Y equals the original amount A, 23,000 times 1 minus the rate of decrease, 1 minus 0.01 raised to the t. Don't write this down. Right? When I load 2030 up into t, that is wrong. That will give us a totally ridiculous answer. Okay, yes, the year is 2030, but how much time has gone by since the starting point, right? This 2300 goes with the year 2020. For the year 2030, we are now 10 years away from where we started. So that's t. That's the amount that goes by. So t is actually 10, right? With your baseline coming in 2020, the year 2030 is 10 years later. The fact that the calendar year is 2030 is irrelevant to the calculation. It's how much time has gone by. And again, simplify this, 23,000 times 0.99 to the 10th. And I'm going to run that through the magic number machine. You can do the same. Make sure you get the same thing. 23,000 times 0.99 raised to the 10. And looks to me like that is, okay, here's another thing about numbers. This is going to be silly, so don't write it down yet. The number I get back is 20,800.7877. So let's say I round that off to 0.79. Okay, way at the bottom of my screen. Even that is a silly number to report as the answer to this question, because what are we counting? We're counting people, right? 20,800.79 people doesn't make any sense. So what we want to do in that case is remember the context and just say, you know what, if it got up to 20,800.79 people, let's just say it got to 2,800 because we haven't added a full people on top of that. So we'll just call it 20,800. If you wanted to round it up to 20,801, nobody would argue, okay? But you don't want to report decimal people. That would be ridiculous. All right, so far so good. All right, so we're going to move forward regardless. So let's do scenario number 3. Annual sales for a company are at $149,000 currently. They're increasing at 6% per year. What are annual sales 7 years later? We are going to use the growth equation for this. So y equals, I'm writing it down, you'll see it in a second. Right, this is a growth problem, so we are going to do a times 1 plus the percentage growth raised to the t, and I'm not going to list the values separately. I'm just going to grab them and put them in. Let's see, the starting amount, 149,000. The growth rate was 0.06, 6%, which is 0.06 in decimal, and we are asking for the new annual sales value 7 years later. So there we go. So 149,000 times 1.06 raised to the 7th. Number machine, 149,000 times 1.06 to the 7th. And that comes out to be, for me, 266,836. Now, we are talking dollars, so it would be reasonable to round to cents, to 2 decimal places. So the decimal is 0.306784, etc., etc. I'm just going to make this rounded to 0.31 for 31 cents. Right? These are dollars. So the new annual sales amount has increased from $149,000 to $266, almost $267,000 for this scenario. Shoot, still getting confused by which screens I want. Okay, last one. The value of, go look along the windows in the classroom. You see all those giant algebra books that weigh about 80 pounds a piece? Let's say that the value of one of those is $125. Those things are like gold. Okay, now nobody's going to pay you $125,000 or $125 for one of those, so don't start stealing them. This is just a for instance. Okay, let's pretend that the value of any one of those books is $125. And the value of that book is going to start decreasing at 10% per year. How much is one of them going to be worth in 5 years? Okay, so think, is this exponential growth or exponential decay? While you're thinking about that, I'm going to prepare. All right, that is exponential decay. The value is decreasing every year. And I'm just going to go ahead and load these numbers up immediately. Remember, the slide said that these books are currently worth $125 a piece. They are decreasing in price, in worth, at 10% per year. So R, the rate, 10% in decimal is 0.1. 1 minus 0.1 is 0.9. The other way to think about that is that every year the book is only 90% the value it was the year before. How many years did we want to go by? We wanted to go by 5 years. Okay, 125 times 0.9 raised to the 7th, and that is a whopping, again, this is dollars, so I'm rounding to the appropriate digits for cents, pennies, $59. The decimal is 0.78711, blah, blah, blah. To round that to cents, I want 2 decimals, so 0.787 is going to round to 0.79. So after 5 years, that thing that was worth $125 is now worth $59.79. This is not a lucrative business. That's why they always update to new editions, so that they can keep charging more and more and more. All right, so that is exponential growth and decay problems at this basic setup. So for today and today, I'll give you'll have a worksheet online that'll have a few of these problems of your own you can try to set up and solve. Tomorrow, a compressed period, so there will just be something there that you can tinker with to review things that you've been doing the last few days overall. Just a quick review of exponential growth and decay, or exponential functions in general, just to make sure you're still up to speed. And then I believe Mr. Childress will be taking it from there on Monday.